Okay, let's start. So this is lecture 30 and it is the last lecture of this course of new material. A couple of announcements. So next week there will be 2 tutorial lectures. Those will not be videoed. So if you want to attend them, you have to come in person. One is on Monday, one is on Wednesday. Both are in the main building in the physics seminar room 31. Okay, it's put up on the website, on the blog. And Monday it's at 6:10 we'll start. Somebody has to come there from a class. Is that you or yeah? So we'll wait for you and then we'll start. And on Wednesday it will be at 4 p.m. usual time, but there. Okay, if you have questions about anything in the course, please prepare them and bring them with you. Okay, or send them in advance. Good. So today we are going to complete as much as possible our discussion of higher order corrections, perturbative corrections in quantum field theory. And let me start with a formula that we derived last time. This formula I didn't actually write down, but let me write it now and then explain it. So what I did last time, and to some extent the time before, was to focus on evaluating the I integral. And this here I am putting together that answer to give actually the matrix element, which we didn't do. So what we focused on evaluating was one single integral for a particular I of p, and that gave me 1 over this whole and minus 1 over 16 pi squared log of delta over this. Now I've added it over 3 different values of the momentum argument. One is where the momentum was k1 plus k2, so its square is s. In the other one, momentum was k1 minus k3, so its square is t. And in the third one, it's u. So when I add the 3 divergent parts, these divergent parts don't depend on momentum, so it just get a factor of 3. And when I add the finite parts, I get a log delta for each of them. Okay. Now there were some i's here and here, but m was defined with an I, and that was a good idea because now there's no I in the formula, and from now on there won't be any I in the formula. So that's a very good thing. Good. Now the question is finally, which we have been postponing for a long time, what sense can we make of this? Okay. As it stands, it's cutoff dependent. Let me say that now, from now on, in today's lecture, I'll only be talking of dimensional regularization. Everything I say can be redone in momentum cutoff, but I warn you that not everything goes through exactly the same way. It's only in the final result that we see the independence of under choice of regulator. So the intermediate steps will be different in some details, and so I can't, since I don't have time to do both and or even don't have motivation, so I'm only doing this one, dim reg, because it's the important one. Okay, so what use is this? What use is this for reality? Now it's divergent. Now reality, there are many levels of reality. The best level is the standard model, which many of you are learning about in a different course, in Arun's course. But for me, I'll just assume that somehow 5/4 theory has an experimental realization. So that assumption is not literally true, although it is realized in some sector of the standard model. But everything I'm doing, except for the detailed answers, goes through in a similar way in other theories. And I think Arun is also doing similar calculations in QED, for example. So we have to imagine an experimental world where this theory actually exists, this field theory of a real scalar field with a 5/4 coupling. and we simply will assume that in that world we can measure things, and then we can, in this field theory path integral approach, we can calculate things, and our goal of course is to compare. So you can do comparisons both ways. Either I calculate something and then I measure that thing and see it agrees or not, or I measure something and then I try to calculate the same thing. So but you want some calculation to agree with some measurement, and this calculation, since it's finite only when epsilon is non-zero, can't possibly agree with any experiment. Okay. Now the first observation that tells us that this is not complete nonsense is a very simple one, and it's the basis for everything which will follow. Let me calculate from this the difference of the matrix element M for momenta S, T and U. So I'm using S, T and U as a proxy for the momenta K1, K2, K3, K4. You can either call it Ki or you can call it STU. Let me pick some reference value S0, T0, U0, and let me subtract the matrix element for an arbitrary set of momenta from the same matrix element for a reference set of momenta. Okay, what is it? Well, this formula allows me to do that. Minus lambda is common in both of these, so it cancels. Lambda squared by 2 times 3 over 8 pi squared epsilon is also common on both, so it also cancels. Log of 4 pi e to the minus gamma e is also common on both, so it also cancels. And the final answer is minus lambda squared by 32 pi squared integral dx from 0 to 1 log of delta of s upon delta of s0. Remember, log of this minus log of that is just log of the ratio. And that's the answer. Now this is really interesting because it's a finite answer. You can actually calculate this. It just requires some ability to evaluate an integral, but again it's an integral from 0 to 1. In worst case, if you can't do it, your computer can definitely do it. Probably your mobile phone can do it. These are not difficult integrals. Okay, everything is known here. The mass parameter is in the Lagrangian, lambda is in the Lagrangian, and we know the answer. Okay, so this is really remarkable. Why? Because, okay, this doesn't determine M, which was the problematic thing. But if I know M at one value by experimental measurement, then this difference will determine it at all other values of ST and U. Now, how many values of ST and U are there? Infinite. I cannot do infinitely many experiments, but with one calculation, which we've done actually here in this course, we know M of ST and U as long as we make one experimental measurement of M, S0, T0 and U0. That's really, really beautiful. So, now, as I said, we are not going into the details of how you measure M. You actually don't measure M. M is a part of the S matrix, the interaction part. What you measure are usually cross sections, but from those you can read back and try to get M. Okay, I'm not going to go into that. I'll assume that because M is a physical quantity in particle physics, and so I'll assume that there's a measurement which can tell me M for any STU that I'm capable of preparing in the lab. Okay, but all I need is one measurement in order to know MSTU for all others, and this is very striking. Okay, let me also notice one thing. Supposing I was not so clever to do perturbation theory to second order and lambda, which we have spent all our time doing in the last few lectures. Supposing I was so lazy that I could only do the lowest order, which is, remember the diagram this. Then I would get a prediction from my first order perturbation theory that m is a constant independent of momenta, and therefore of course this difference would be 0. That's why this term has dropped out from this formula. Okay, that would be a wrong conclusion. So it means that to know the fact that m depends on momenta, I need to go to second order perturbation theory. First order gives me a misleading idea, which is approximately true, that this m is independent of momenta. I say approximately because actually you know that log of things, delta depends on p squared, so it's linear in S, and log of such a thing is a slowly growing function. So that function, if we somehow didn't know that it's changing, then we would just, so we are not surprised that, well, when lambda is small and you have a slowly growing function, we simply don't know this term if we work to lowest order, and the term kicks in when we work to the next order. But of course, it's significant and measurable. Surely this is such a thing is measurable. So that's one realization, that we need one experimental measurement in order to bring our MSTU at second order to be a real thing that we can actually use to predict experiments. Does this remind you of anything we discussed earlier in this course? Normalization of the path integral. Thank you. Very good point. If you remember, there also we made a comment that out of all problems where a particle moves in one dimension under a potential v of x, if we just fix by any other means, in that case not by experiment but by operator language, we fix the propagator u from xi ti to xf tf. Then by ratios we can fix the determinant and the measure, therefore, for any other potential. And that's again, it seemed like we were losing something because for one result we had to go elsewhere, but we got infinitely many other results for free, as it were, and something similar is happening here. Good. Okay, now to make this point a little sharper, we have to ask a different question. How do we know this? We've never asked this question in this course, and the question is sort of trivial at lowest order, working at lowest order in perturbation theory. Why? Because lambda, apart from a minus sign, is the same as m. So to know lambda for my theory, I should do one measurement which will tell me what is lambda. Okay? Then only I know it. I can't know lambda abstractly. It might be 0.1, it might be 0.01. It's the analog of knowing E, the electric charge of the electron. I can't just guess it. To do quantum electrodynamics, I have to measure E. But how do I measure E? By measuring a matrix element. There's no other way to measure E. Anything you do, even Coulomb's law, is a matrix element. Okay? And Coulomb's law is an example of an amplitude, of extracting a result of an amplitude which will have quantum corrections to higher orders. So it's only in, just like this is the same as this in lowest order, in electrodynamics there's an amplitude which is the same as E squared by 4 pi, the fine structure constant, in lowest order. Okay, but in higher order it depends, it has corrections, and the corrections depend logarithmically on the energy at which I'm measuring them. So same thing happens here. So by measuring m.
So we need at least two measurements of m, right?
Why do we need two measurements of m?
One for the second term.
Yeah, it looks like we need two measurements, one to subtract this and one to determine lambda. But as we'll see in a little while, that's not really how it is. It's a little more subtle than that. It's really one measurement. Once we determine lambda, in some sense, we already know this. So let me explain that. Okay. Now, now we have to face the following interesting fact. Supposing we did measure m at some fixed value of st and u, would I get lambda directly? No, I would get minus lambda plus lambda squared times all that. I would have to use it to solve for lambda in terms of the thing I measure. So what is lambda? Lambda is the parameter in my Lagrangian. Physically, what does it mean? Can I measure lambda directly? No, I'm not measuring lambda directly. I'm measuring this, and from this I'm calculating lambda by this relation. What?
Coupling between fields.
Well, it's the coupling between fields in the Lagrangian, but what is it in nature?
First order is scattering.
Well, nature doesn't know about first order. Nature just does scattering. Nature doesn't sit and say, I'm going to, if you do this experiment, I'll give you the answer to first order. Nature just gives you the exact answer, right?
Low energy scattering.
In classical regimes, you would expect that to be.
Classical regimes, low energies, all this is true. But now that we are working in this order, in that case, we shouldn't be working in this order. In that case, we don't need to ask this question. It's true that we got this far by working in classical regimes and thinking that lambda is m or E squared is m, and that's the end of the discussion. But now we have added this term. So obviously we are not in the classical regime where this term would be irrelevant. We have added the term and we want to know how to make sense of it. And it's this term which is divergent. So if we didn't add it, we were happy. Now that we've added it, we are unhappy. But we can't go back and say, well, lambda is approximately the low energy coupling. It is, but it's what is it in this order of perturbation theory? What is its physics? Can I measure it? And the answer is actually I can't measure it. Okay, lambda is no longer measurable once I've gone to higher order in perturbation theory. I can determine it from a different measurement, but it's not directly a physical quantity. So the first thing we learn here is that lambda in the Lagrangian is not a physical quantity. But here by physical I mean something very precise. I mean something which has a direct physical meaning. Once we go work beyond lowest order. Okay. So this is one thing. This is a consequence. But there's still the so-called elephant in the room, which is that the relation between m and lambda, which is the line at the top of this board, is still divergent. And we haven't really got rid of that. We can get rid of it by comparing things, but supposing we want absolute determination of m, we haven't got rid of this problem. But now we have a new insight. Relation between m and lambda is divergent. M is measurable. If it's measurable, it's not divergent. So instead of saying this equation is bad because m is a divergent function of lambda, we should say this equation tells us that lambda is a divergent function of m. And this is reasonable because lambda isn't a physically measurable quantity. So if it's divergent in the limit that cutoff goes to infinity, we don't care too much. We are trying to predict m. So this is an important input. Okay. So now with all these insights, we can rework how we do perturbation theory in QFT, and that is what gives us the concept of renormalized coupling and renormalized perturbation theory. And I'm going to do that now in the next half an hour. So are there any questions on these three observations? All of them I believe are obvious after we have done this calculation. In fact, first one was always obvious. It was obvious that if m is a perturbation series in lambda, then lambda itself is nothing but an expansion parameter. It's not the strength of any interaction. Second point, it follows from that. And third point, of course, is followed from our calculation. So now let's try to do our calculation again, but with this insight.
So,
Yes.
when we started wrote down the rules to calculate M, we said that we should have connected and also amputated
Yes.
diagrams.
Yes.
And for that we gave the justification that any physical quantity that we measure
Yes.
which is related to M
Yeah.
will have those extra factors which will cut down all those poles and all that, like the 1 by p square plus M square. So
Yeah.
that is why we ignore them.
Yeah.
There we assume that all of the things that we are considering in M
Hmm.
are we have taken all the divergences out because finally cross sections will somehow.
No, we didn't take the divergences out. We took the external legs out. See, what did we take out? We took out the bubble diagrams that we didn't take out by hand. That's because the denominator cancels them.
Yeah,
So
that
they are
is
not
fine.
there.
Yeah.
Now, the only remaining thing is to consider the disconnected diagrams, which are not bubble diagrams.
Right.
Okay. Now, it turns out that they don't contribute to the S matrix. So there is a scattering matrix from where there is a prescription to calculate the cross section, and those diagrams don't contribute to it. Not only that, the external leg propagators also don't contribute, and that's what we dropped. So M is the quantity. Actually, M is such a quantity that the cross section sigma is equal to mod M squared times kinematic factors. You can look this up in any textbook. I assume this would have been done in QFT1. Sigma is really M squared times kinematic factors. So if you want to be fussy, if I measure sigma, which I definitely measure, that's a quantity with dimension of area which literally comes out of analyzing data at LHC or any accelerator. I should remove the kinematic factors, that's not hard. I should take a square root of this, that's a little tricky because I'll get an answer up to a phase. But you know, a phase, what's a phase between friends? This thing is quite real. So we hope for the best. At least in some region where delta is positive, everything will be real. So we have calculated the correct thing, M. M is literally, from this point of view, M is literally same as what you can measure. There are a lot of things that you have to put here to be careful, like delta, momentum conserving, delta function, the flux of particles coming in, and so on. But you know, all of them are knowable. So therefore, really, the information in sigma is the information in M squared. Okay.
Like, the question is just like how the kinematic factors got rid of the external connected, like the legs that were there. We dropped them because we said that okay, when we put it all together, those will drop out, and hence we said that M itself should be calculated without the external legs.
Yeah, so it is that M defined without external legs, which appears in the formula I just erased. Sigma equals mod M squared. So the motivation is that to find the cross section, that M must go.
Okay.
The external legs of that M should go. I mean, M should be defined without its external legs.
And no such like there is no phase space, like there is no such thing that takes care of these divergences, which is why we are interested in the.
Yeah, there's no such thing which takes care of these divergences. That's right. So this is really the basic, the heart of the matter, if you like. And all practical field theories, standard model, Yang-Mills theory, just electrodynamics, all have the same feature, all have logarithmic divergences, and all have an M which will look broadly like this, with the differences that you may have to worry about gauge invariance, you may have to worry about gamma matrices, so the calculation is more tedious. This is the simplified model, the simple model. Okay, now before we do anything more, we have to tackle the following question, which we asked last time. What is the meaning of log delta of S? After all, 4 pi e to the minus gamma e is just a pure number, but we have log of a dimensional quantity, and this is not nice. Okay, and it turns out that it's in our best interest to settle this issue right now. We could proceed without doing that, but things will fall into place more naturally if we settle this issue now. And we'll settle it by noticing the following thing. Our Lagrangian is, as you know, half del mu phi squared minus m squared by 2 phi squared minus lambda by 4 phi fourth. Now, in this discussion, we were in 4 dimensions. And in 4 dimensions, I'm sure you have worked out this canonical dimension of phi is 1. Therefore, the canonical dimension of m is 1 and canonical dimension of lambda is 0. You've done this? You know this? Okay. But this cannot be true in all dimensions. It's a dimension dependent statement because actually the canonical dimension of phi is d minus 2 by 2. Because this whole thing should have dimension d, so that after integrating in d dx to get the action, that thing is dimensionless. It's the action, where the action goes in the exponential and is divided by h bar, but h bar we have set to 1. Canonical dimension precisely means what are the dimensions we get after setting h bar equals 1. So it's pure numbers, but this is the correct answer. And we easily see that m continues to be 1. Because here you have d minus 2 by 2 twice. So from phi's you get d minus 2 and then 2 dels make it back to d. Okay, and del doesn't change its dimension. It's d by dx in any dimension. Similarly, m is 1 in any dimension, and again this thing is dimensionless. What about here? Lambda now will no longer be dimensionless, and in fact in dimension d we can easily calculate that lambda dimension is 4 minus d. Because I take phi to the 4th, I get twice d minus 2, that's 2d minus 4. And then I add 4 minus d, that makes it back to d. So this must be the value of the dimension of lambda. Now we see that I am doing something a little clumsy here. In my perturbation theory, this has dimension 4 minus d, but this has a different dimension, twice of 4 minus d, and both are non-zero and different from each other, but I'm adding them. I'm doing something dimensionally inconsistent, right? So I shouldn't do that. So the solution is, I change my Lagrangian by introducing a scale and putting here mu to the epsilon 5/4, where mu is a parameter with dimension of mass. If I do that, then mu to the epsilon has a dimension 4 minus d. Okay, mass has all mass parameters have dimension 1. So the epsilon power will have dimension epsilon, which is 4 minus d. Remember, our parameter epsilon is nothing but 4 minus d. So if I put mu to the epsilon here, and then I can say that lambda remains dimensionless. I've absorbed the dimension of what would have been the dimension of lambda into this term. Okay. Now, I could have taken mu to be the same as m in order not to introduce a new parameter in the theory. And it's a natural choice. I could do everything in the rest of this lecture doing that. But in electrodynamics, I have a small problem. The photon doesn't have a mass. Okay. So it's a bit unclear, and there are many other masses. Electron has one mass, muon has different mass. Which one shall I put? So it makes sense to just introduce a generic parameter, and actually it turns out to give us some illumination, though it looks artificial at this stage. So I'm going to replace my Lagrangian with this. And what is the effect on this? Well, it puts mu to the epsilon here and mu to the 2 epsilon here. Right? Just send lambda to lambda times mu to the epsilon. Now, this looks inconsistent, but we'll show in a moment that this change, which means this doesn't have same dimension as this, solves the problem of dimensional inconsistency of log delta. So let me show you that. So this new dimensional change solves that old problem, and let's do the calculation to show that. The calculation consists of two things. First of all, we'll take 1 mu to the epsilon out overall, and we'll rewrite this as, let me, I don't want to keep writing that line, so let me do it here. So I'll keep 1 mu to the epsilon out, I'll explain why. Then I have minus lambda plus single power of mu to the epsilon and lambda squared. Alright? This was mu to the epsilon, this was mu to the 2 epsilon, so I took 1 power out. Okay. Next, I'm going to take this and write it as 1 plus epsilon log mu plus higher orders in epsilon. Now, we've always taken the policy that wherever epsilon can be taken to 0, we take it to 0. We already dropped all terms in this expression that vanish when epsilon is 0. And what happens when I do this? Well, this term, it's here, will multiply this and it will also multiply that. But when it multiplies that, this is already finite, so epsilon can be taken to 0. So there's no need to do that. But when it multiplies this, I get a finite term because epsilon upstairs and epsilon downstairs, they cancel. Okay, so the extra term is lambda squared 3 by 8 pi squared log of mu. Right? So this is the extra term inside this big bracket due to the introduction of mu to the epsilon. So I have everything that I had before plus one more term.
So I think there's a factor of 2 missing. Yeah.
There's a factor of 2 missing.
Lambda squared by 2.
Lambda squared by 2. Lambda squared by 2 was here. Then I've been missing that factor since the beginning. Someone should have told me. But yes, I think you're right.
It was there.
Good. Oh, it was there. Maybe I lost it after rewriting things. Good. So 16. Ah, no. Something is wrong. Let me just... it's okay. It's okay. I think this is okay. Good. So I'll keep it like this. Lambda squared by 2, 3 by 8 pi squared. So this term I have to add to all the terms in that bracket because lambda squared by 2 is outside and this I've expanded. So this will be gone now and this is my extra term. Okay. Now this term is the same as minus 3 by 16 pi squared log of 1 by mu squared. Minus because I replaced mu by 1 over mu and then I took squared. So this is twice what it should be. So I compensate by making this 16. These two things are the same. Now I see that I can add, so there are 3 copies of one term, 1 by 16 pi squared log 1 by mu squared, and I can distribute them into these 3 terms. And so finally, what it will do is give me mu to the epsilon overall outside, lambda plus lambda squared by 2, 3 by 8 pi squared epsilon, minus 1 over 16 pi squared integral 0 to 1 dx log of delta of s upon 4 pi e to the minus gamma e mu squared plus the other terms. Lot of brackets to close. Is that clear? This is an additive term. It adds to the things which are inside lambda squared by 2. And it has minus 3 by 1 over 16 pi squared, but this is minus 1 by 16 pi squared. And there are 3 terms. So I'll stick my mu squared into each of the terms. And when I add this to this inside log, they basically multiply. And so I get them in the denominator. And now you can see a very nice thing has happened. This is dimensionally consistent. Lambda is dimensionless, so I can add it to lambda squared. And delta has the same dimension as mu squared. So now it has become dimensionally consistent. So this is the way we'll work. Okay? So you understood what I did? I scale lambda to absorb its dimension away from 4 dimensions. Then I expanded this and I noticed the only contribution comes when this epsilon hits the pole and gives me a finite part, and I absorb that finite part into that. Okay. Good. So this is my M of STU now. And if I want, I can rename this thing as some mu tilde squared, and then I have log delta over mu tilde squared. Okay. I haven't done anything to the divergent term. I've just made the delta terms dimensionally consistent. Very good. Okay, that's done. Now we come to the question, what is physically observable? So for that, I said we have to measure M, and from that determine what is the coupling strength of the theory. So what I am going to do is say that we measure M at a fixed value S0, T0 and U0 and define a new quantity which I'll call minus I mu to the epsilon lambda r to be nothing but I times M at this value. Actually, I don't know why I put these i's, they are not needed. So, you see what I've done here? I've taken this, evaluated it at a specific value S0, T0, U0, and I've defined it to be minus mu to the epsilon times a new quantity lambda r. Why did I choose mu to the epsilon? Because it cancels that one which I took out. And why did I choose minus? Because lambda r at lowest order is lambda, but corrected. So lambda r has a name, it's called the renormalized coupling. And this is true to what we just said a few minutes ago, which is that the only coupling you can really measure is the one obtained by measuring M. So it's sensible to call this result of this measurement at some fixed momenta to be lambda r. The only thing we did was to scale out that dimension in keeping with our scaling of dimension of lambda. And so from this, we see that lambda r is equal to lambda minus lambda squared by 2, 3 by 8 pi squared epsilon, minus 1 by 16 pi squared. Now I can't keep writing this whole integral and stuff so many times, so I'm going to call it S of f of s t0, s0, t0, u0. So my definition of f of st and u is simply integral 0 to 1 dx log of delta upon mu tilde squared of s plus same thing of t and u. So I'll just use this simplified notation and that's it. So this whole thing, after getting a mu squared in its denominator, I'm calling it f. So f depends on mu. And this is a crucial relation. This says that the physical measurable coupling lambda r is related to the Lagrangian parameter lambda by this relation.
Sir,
Yes?
shouldn't there be a mu epsilon like earlier there was a
No, I think I got rid of all of them. So this one, there were two. There was one here and one here. Which one are you referring to?
okay, you took the log.
This one I got rid of by replacing it by 1 plus epsilon log mu, and that log mu cleverly went in and sat under delta. So it's gone. This I used up. This one is there, but in my definition of lambda r, there's also mu to the epsilon. So the left side also has a net mu to the epsilon and also a net minus sign, and that's how I got that this is this and the other term contributes with the minus. So everything is consistent and there is a mu dependence, but it's all inside f. Okay, f is this. Good, yes.
We want this to be true for all orders in lambda, right?
Well, so this is the point. Before I mentioned this before, but it's a good question. We have to decide to what order in perturbation theory we want to work before we start doing anything. If we wanted to work to lowest order, then lambda r was lambda, and I was wasting everybody's time trying to define lambda r because, well, it's just lambda. So if you like, this is all of non-quantum corrected physics. Whatever is non-quantum corrected physics, lambda r is lambda, and we are done. Now we've decided to work to order lambda squared. Why? Because we had the courage to evaluate a one loop diagram. If you were brave enough to evaluate the two loop diagram, there would also be a term lambda cubed. But in that case, the relation between lambda r and lambda would be that lambda r is lambda minus lambda squared times this plus lambda cubed times whatever your calculation would have given, but again evaluated at S0, T0 and U0. So the relation between lambda r and lambda depends on the order of perturbation theory to which I am working. That's important. And so it's only this relation and this order. Now this precisely brings me to my point. Because we are working to this order, now I hopefully don't need this expression anymore because I have m over there. Precisely because I am working to this order, I can invert this to write lambda is equal to lambda r plus lambda r squared by 2, 3 by 8 pi squared epsilon minus Do you agree with this? If you are trying to solve a quadratic equation to solve for lambda in terms of lambda r, you are making a mistake. Because to lowest order lambda r and lambda are the same. Therefore, the order of lambda squared is the same as the order of lambda r squared. If I am dropping terms of order lambda cubed, then I must drop terms of order lambda r cubed when I invert it. Okay. This is one of the most minor issues in this discussion, but it's one of the most commonly confusing ones. So this is the correct inverse of that. The only valid objection you could say is, well, didn't you say epsilon is very, very, very small, like so that d is almost 4, so this is like almost infinity, so then how is this even small? But this question you should have asked me long ago. Because if this is large, then why have I worked only to for one loop order? Why didn't I do lambda cube, lambda fourth? I could have declared that, well, this number is so large that this second order perturbation theory is a failure. So there's an order of limits in our mind. Lambda is smaller than anything, and epsilon is taken to 0 only after carrying out renormalized perturbation theory, which we are doing now. So we treat this as a finite number such that any power of lambda in front of it is small.
Sir, so lambda
Yes.
is equal to lambda to the leading order.
Yes, it's equal to lambda to the leading order, and therefore the inverse also is that
Yeah,
way.
so this lambda which you will obtain
Yeah.
is the one which you will obtain from low energy scattering.
Not necessarily low energy, just any fixed S0, T0 and U0. I choose it, and the relation depends on that.
So but that won't guarantee that lambda r is equal to lambda, right?
It's not equal to lambda, it's
I mean,
equal to
the
lambda
leading-
minus
to
this
the
term.
leading order. Lambda r and lambda
To
will be-
leading order, because to leading order means I neglect lambda squared.
Yeah.
Yes. If I neglect lambda squared, then lambda r is equal to lambda.
No, so then I got confused. How did we say that since lambda r and lambda are same?
No, they are not the same. Lambda r is equal to lambda only to leading order, but we are working to next to leading order, so they are not the same. I gave you a comparison of what would be true if we were working to first order in lambda, but that's not what we are doing. We are working to second order in lambda. If we weren't, then why did we calculate all those one loop diagrams? We have decided to work to second order, neither third order nor first order. The only point is that when we work to second order, it's good to check, as just for our sanity, that if we neglected from second order, you can always go to first order by dropping the second order term. Any series which I evaluate to high order, I can always drop those and evaluate the low terms if I want, just for a check. And I notice that these are equal in first order. That means that they are of the same order of magnitude. Therefore, here dropping terms of order lambda cubed when I invert corresponds to dropping terms of order lambda r to the cubed. You can also check it by solving this quadratic if you want to. Call this whole thing A, solve the quadratic, expand it, and then see whether it makes sense to keep higher order terms. The problem is that any term in this which is higher than lambda r squared is a term about which you have lost information because you never computed these loop diagrams to that order in lambda. Good. Okay. So this is the relation between lambda and lambda r. And now, yes.
So earlier you said that lambda is the diverging function of scattering on the
Yes. And here lambda and lambda r are divergent function of each other. We have not yet decided which one is finite and which one is divergent. It's just that each one is a divergent function of the other. Divergent in the limit epsilon goes to 0. I'll come to that. I'm going to discuss that. Now that we have this, I can take m, which is expressed as a function of lambda and lambda squared, and I can insert over there lambda as lambda r plus this function times lambda squared. So therefore I can express m in terms of lambda r. Okay? Is that clear? M is expressed in terms of lambda, lambda is expressed in terms of lambda r. So therefore m can be expressed in terms of lambda r, and let's write down what we get when we do that. The answer is, now by the way, yeah, so it's the same thing. It's this one with the substitution lambda is equal to all that. Okay? I think I made some error somewhere. Here is a minus. Thank you. Here is a minus. Yes.
No, there would be minus lambda plus lambda square.
Oh, yes. True. Thank you. Yes, that is correct. That's the minus. Okay. And if we express it in terms of lambda r, we find by simple calculation that we get minus lambda r minus lambda r squared over 32 pi squared f of STU minus f of S0 T0 U0. So I'm sorry, you have to look at this board in the following order. This is m. After we shifted lambda with this factor to make it dimensionless, and also took this factor and expanded it and absorbed it there. Then this is the definition of lambda r. Actually, it's not. We defined lambda r in terms of m, but this is the result of it. Then we invert it, and then we re-express m in terms of lambda r. And now we have finally some kind of payoff. We see that m from this equation, m STU is a finite function of lambda r. You can see that there is no divergence in this expression. You can also see that this f STU minus f S0 T0 U0 contains these logs of delta of S over delta of S0 and so on. So you might say, well, what have I done new which is different from my starting statement today, that I can compare two m's at two different values, STU and S0 T0 U0, and if I subtract them I get a finite answer. This looks like the same finite answer. Not exactly. It's close, it's in spirit it's the same, but we've done something different. And why is it different? Well, first of all, we've got an answer for m, not for m minus some other m. This is actually the answer for m. The price we paid was to get rid of lambda from the discussion, which is the parameter in the Lagrangian. Okay? So we found that there is a more physical parameter lambda r, which itself is related to lambda in second order by a non-trivial equation. And if we express m in terms of that one, then we get a finite perturbation series. And this is the basic idea. Now, remember lambda r was measured. So we can simply now decide that, well, we fix S0, T0, U0, we measure lambda r. Now we know everything on the right side of this equation as a function of S, T and U. There are no unknown parameters anymore other than, okay, the mass of the field, which we somehow hope we also know. And we have a prediction for the amplitude at all, for all momenta, and it's a finite prediction. So it's no longer, so we have exchanged that idea of subtracting from m its own value at some other momentum for the idea of defining a new coupling constant.
So we defined m of s naught t naught u naught as minus lambda. So that was the
crux.
Is how we'll
Yes.
determine lambda.
Yes.
So that is why we need only one of
Yes.
them.
But actually, there's an interesting further twist to it. But unfortunately, that's okay. So I'm just going to say a few more things and then end this lecture, and that's all the portion for this course. But in my notes, I'm giving you 2 more sections for your own entertainment, in which I'll point out that actually this is entirely up to us, because again, what is it? It's a finite piece which doesn't depend on the momenta of my interest. So actually, I can choose this as I like. And this is the concept of renormalization scheme. That's a little too advanced. If I had like 4 lectures or 3 lectures, I could have discussed renormalization schemes. So it turns out that even this factor, whatever it is not absolutely essential in the discussion. But that's a next level statement. So for us, m is expressed like this, with precisely a measured parameter measured at these values of momentum. This, by the way, this is a renormalization scheme which has a name. It's called momentum subtraction scheme. And you can see why it has that name. The way we define things, it came out automatically that when we define lambda r at these values of st and u, then this term came automatically. There's an alternate scheme where that term is just dropped altogether, and this is still a correct equation. So renormalization is, in short, quite subtle, and there are many ways to do it.
So
Yes.
The m is originally we had a very sort of scale independent quantity.
Hmm. Now it's scale
Now
dependent.
Now
Absolutely.
it is very like it's manifestly
Yes,
scale
yes. And the answer to that is also very interesting, and again it's part of the optional notes. The answer to that is, let's look at m in terms of lambda r, the boxed equation. Now we don't need any other equations, so I'll delete other equations. How does m depend on mu? It depends on mu because what? It depends on mu. So there should be 2 dependencies of m on mu. Can huh?
The factor of mu to the epsilon, right?
No, factors of mu to the epsilon have all cancelled.
Epsilon is taken.
There's no, this is the correct equation. Okay.
ln by mu squared, that will be.
Yeah, so this has mu squared, but I think that cancels with this one. So actually there's, yeah, so, okay, look, let me not go into this. The fact that m is fundamentally independent of mu leads to what is called the renormalization group equation. I think Arun might be planning, so those of you who are going to be in his course, who are in his course are going to probably see this later this week or next week. But I think, let me not do this, because you know, whatever I am telling you here today, I've tried to make a clear story, and every step of this is precise. I don't want to tell you general things which I don't have time to go into. But ultimately, yes, it does introduce a scale into the theory. It's called the renormalization scale, and that mass scale is up to me to choose to make my perturbation series as good as possible. What will happen is that lambda r will naturally flow with that scale, and the smaller I get lambda r, the better my perturbation series will be, because I am dropping terms of order lambda cubed onwards. So I induce an error by doing that, and if lambda r is not too small, then my error is bigger. So renormalization group is a way, if you see it in this language, to minimize the error in the perturbation series. Okay, so the last thing I want to discuss is counter terms, and this again is repackaging the result. So if you think the only result in today's lecture was the first one, which said that if I take the difference of 2 m's, I get a finite answer. The definition of lambda r is just a repackaging of that statement, which says more carefully that m itself should be viewed as a function of some physically measurable parameter, not of the parameter lambda in the Lagrangian, and as such it's finite. This relation is finite, epsilon has gone away from it. By the way, you really need to derive this from the relation of m in terms of lambda that we had derived last time, and from the relation of lambda to lambda r. You need to work this out and convince yourself that's the correct answer. Okay. Now, from now, we'll actually give lambda a new name, lambda 0, because there's a lambda r and a lambda 0. Okay, so we want to distinguish them. Lambda 0 is the parameter in the Lagrangian, and lambda r is the renormalized parameter that we defined. Okay, but in fact, lambda 0 is equal to lambda r plus delta lambda r. We wrote this relation earlier, where I've just separated two terms, where delta lambda r is lambda r squared by 2, 3 over 8 pi squared epsilon minus 1 by 16 pi squared f of S0, T0, U0. So this was the equation I wrote before, lambda r plus that is lambda 0, should be still here. I've just broken it in two parts, lambda r and delta lambda r. Now let's revisit my Lagrangian. In my Lagrangian I have this, and where I had lambda 0, this was what was in the Lagrangian, I'll replace it by lambda r plus delta lambda r. So I have lambda r over 4 factorial 5 to the 4th minus delta lambda r over 4 factorial 5 to the 4th. Trivial statement, I just put it in the Lagrangian, so that my Lagrangian now depends directly on lambda r and not on lambda 0. But remember, delta lambda r is cutoff dependent. So I made my Lagrangian cutoff dependent. Okay, I don't mind making my Lagrangian cutoff dependent as long as the physical quantities that it predicts are cutoff independent and finite. And that's exactly what happens. But now the structure of perturbation theory becomes a little different, and that's very beautiful, and it actually simplifies everything. So once you understand this, you can almost forget about most of the things we did before. How will I do perturbation theory with such a Lagrangian? Well, this is a 5/4 vertex and this is another 5/4 vertex. Okay, so how will I calculate 4-point diagrams? I'll say, well, I can have connected diagram here of strength lambda r. Okay, now I'm going to second order, so I should of course add to this these diagrams of strength lambda r squared, because there's one factor here and one here, so this is of order lambda r squared. So going to second order in lambda, this vertex has given me two terms, of which this term is finite and this term is divergent, because it's the same function of lambda r as we already calculated using lambda, so it's obviously going to be divergent. But now there's this new term, this goes by the name of counter term. And I have to calculate Feynman diagrams using this, because this is also a 5/4 interaction. The only clever thing is to note that delta r is of order lambda r squared. So this diagram with delta lambda r at its vertex is already of order second order. And now can you guess what? And there are no more diagrams, because if I take a loop diagram and put delta lambda at one or the other place, I'll get at least lambda cubed, and I'm not going to that order. Okay, now can you guess what will happen when I add all these? The divergence from here, coming from a loop calculation, will cancel the divergence from here, which is already built into the Lagrangian. It's just again a way of reorganizing things. So, but it will leave behind a well-defined finite part. And now you can sort of understand what is the goal of renormalizing a quantum field theory. It's to develop an algorithm by which, by adding counter terms to the Lagrangian in every order of perturbation theory, I can render all perturbative calculations up to that order to be finite as functions of lambda r. And that's it. So this is called renormalized perturbation theory. It's not that different from the previous one. We already got an answer for m in the previous one in terms of lambda 0, and then we eliminated lambda 0 in terms of lambda r. Here, our answers come out directly in terms of lambda r. We don't just have to do that extra step of eliminating lambda 0. It's never there. But instead, the extra step is there's a counter term Lagrangian. And now this thing is of order lambda r squared. But if I was working to third order, then this would have another contribution of order lambda r cubed. So my counter term Lagrangian must be determined to every order. So you might ask, what did I gain by doing this? Well, here's an interesting answer. This Lagrangian, I claim, has not just finite 4-point function, but finite all n-point functions. Supposing I wanted to calculate a 6-point function, which gives me an amplitude for scattering 2 particles and which with 4 particles coming out. It's a different physical process. I don't need to measure that one at some fixed momenta and subtract. I simply calculate that in this Lagrangian to the same order. It will be finite. This is not something completely obvious, but it can be proved. So renormalized perturbation theory has the property that once you have done it, everything you calculate is finite. The last thing though, I have lied about one thing. We did not discuss, and they are important. At least they'll be important if we go to higher orders. Mass and wave function renormalization. So this is a confusing word, but really field renormalization. So it turns out that even this mass term needs to be replaced by an mr squared and a delta mr squared. So there's a different renormalized mass from the bare mass, and the field phi also, there's a different renormalized field from the bare field. So actually the full renormalized Lagrangian should be a function of phi r, mr and lambda r with counter terms, one for each of them, for each of these terms. So there'll be a delta mr squared times phi squared. There'll be also a counter term that renormalizes the field, and it's that one that will give me finite answers for everything. So I cheated a little bit because we only had time to discuss renormalizing lambda, but these are 2 other parameters that do need to be renormalized in a field theory. Yes?
Coupling and mass having some physical value, like we can think of that as a measurement.
Yeah.
What does phi r mean?
Yeah, so phi r is a subtle thing. It's an interesting thing. The fact that phi gets renormalized actually changes its scaling dimension from its classical value by a quantum amount. So the quantum corrected scaling dimension of phi is different from its classical value, and this actually helps us to determine the scaling behavior of correlation functions. So it is important.
Scaling as in
The dimension, the canonical dimensions we calculated, those were all valid in classical theory, and now they'll be changed in the quantum theory.
So like we had some lambda into mu of epsilon.
Yeah.
We have to do similar things.
We have to do similar things for phi as well as for m in principle, and then we extract some renormalized parameters. The difference though is that lambda is the expansion parameter. Neither phi nor m is an expansion parameter. Lambda is playing a double role, which is why it was so confusing, this whole discussion. Because on one hand, it's a coupling strength, which means we want to measure it. On the other hand, it's an expansion parameter, which means we want to expand in it. And then we realized that all along we were expanding in the wrong parameter, lambda 0. And that's the reason why the field theory had divergences. If once we expand in the correct parameter, we don't have divergences. Yeah.
Lambda is now a finite number, right?
It's a
It could
finite
be
number,
large
yes.
also, then
It could be large, and then of course everything I've done fails to work. So perturbation theory breaks down whenever, so you can actually tell by an experiment when your perturbation theory will break down. If somebody says, look, I have to measure m in order to determine lambda, and I measure m, and in suitable dimensionless units it turns out to be 100 instead of 0.1 or 0.05, then everything we did didn't make sense in the first place. So we shouldn't expect anything to work. Which leads to many interesting questions. For example, there could be some values of STU where M gets large. There could be other values where it gets small. Okay, so perturbation theory only works in the regime where M itself is small. So that this is all part of this issue that lambda is simultaneously a physical quantity and an expansion parameter. These two things are quite tricky to make them fit together. Yeah, question?
So, renormalization as a scheme is only for perturbation theory.
Yes, at least in the way I've discussed. So I've discussed perturbative renormalization. There are broader ideas of renormalization. There are also ideas of renormalization in condensed matter systems. There is position space renormalization for spin systems on a lattice. It's a very broad subject. I could tell you a lot about it, but I think we are out of time today and also in the course. It's a very broad subject. So this is perturbative renormalization only, and this is only as far as we can get. If you go on the archive, I do have a set of full lecture notes on still perturbative renormalization, but you might find more general details. You might find more details in that compared to these notes. Good. So with that, we are done with all the new material for this course, at least 2 weeks ahead of your exam, which I hope you see as a good thing. More than 2 weeks. Today is 4th April, 3 weeks before your exam. So I'm very happy about that. But next week we will meet on Monday and Wednesday as planned to do a tutorial. So I'll stop there.